Okay, so far we have learned about force diagrams, we've learned how to calculate the force of gravity, and then we've also learned how to evaluate a force diagram to solve for the values of other forces in the scenario given some information. We've even gone through looking at forces that are at angles, such as the force of tension, a normal force being applied, but what we haven't done was looking at angled forces on ramps yet. This is because although it's the same set of problem solving skills that you're going to use, it is a little bit different frame of reference for us. So let's just kind of review what we learned to follow along with the sheet. We have learned that the attraction or pull between two massive objects, aka the force of gravity, is always in the direction pointing to the center of the object causing that force. Since the Earth is so massive and we look at things from our perspective, the FG of objects on Earth is always down. Remember back to last unit when a cart was placed on a frictionless ramp. We saw that the cart accelerated. If there was the ramp, there was the cart, and it accelerated. What was responsible for the cart's acceleration down the ramp? Most of you during that lab had said something along the lines of gravity. Gravity was causing the cart to go down the ramp. And it was partially due to that gravity on the object. But all of the gravity wasn't the net force that caused the acceleration. Remember, net force needs to cause an acceleration, and it wasn't all of the gravity that was the net force. It was just the part that was in the same direction of acceleration. So if we look back to our diagram, the cart accelerated in this direction. So that means we needed to look at a net force that was in that direction. Because of this, we need to change our frame of reference and find the component or part of gravity that caused this acceleration. So find that net force on the diagram to the right. The diagram to the right would be assuming that this is Fn and this is Fg. Originally, we were really inclined to break up Fn, as we see that's on an angle, into its components. However, knowing that our acceleration is actually kind of down and to the right, it's not going to be the components of Fn that are causing this acceleration. It's actually, like you said, gravity, but it's only part of gravity. So in order to view gravity on an angle, I tend to tilt my paper until the normal force is pointing straight up. Once the normal force is pointing straight up, I can then see that gravity looks as if it's on an angle. Now I can draw in my components for gravity. So this looks about 4 blocks down and 2 blocks over. With our convention, if I were to label these forces or these components that make up the force of gravity, I would label this one FGY and FGX. Going back to the question right here, it asks which or what component is the net force. If I look at FGY, it has Fn up. That will cancel out with that vertical component of gravity. Since those are the same size, those cancel out. That's not our net force. Additionally, if we remember back to the scenario, the acceleration was in this direction, so the net force needs to be in that direction. The only force that's left for us to consider is the horizontal component of gravity. Sometimes you'll see these referred to, if you're looking on online texts or any other sources, sometimes you'll see this referred to as the perpendicular value and the parallel value, but X and Y are fine for us in our class. So this FGX was the portion of gravity that caused the acceleration of the object. Going back to our scenarios, we still won't be looking at accelerating objects this unit, but next unit we will. But this still helps us think critically about scenarios where an object is on a ramp. Going back to our notes, so this means we will consider gravity to be at an angle. And that is only for ramp situations. or inclined planes as they're commonly referred to. Okay, looking at the example below, it says an 8.5 Newton box of cake mix is sitting at rest on a binder below. Draw a force diagram and solve for the normal force and the force of friction. Write a net force equation and then solve for those kind of things. This will take us through. As we start, we would want to circle our system, so circling that box. Our normal force needs to be perpendicular to the surface. Here's our surface, so here is perpendicular. And if you notice, the grid that has been placed behind actually was tilted to make sure that your normal force would be matching up with one of those lines. So I'm going to draw my normal force all the way up. Fn. My force of gravity on the object still is straight down. We haven't changed our view of Earth, right? Earth is still below us, so still straight down to the center. And on my diagram, it goes straight down. And this is Fg. We do have one more thing to consider. This box of cake is stationary, it's at rest, so therefore it's not accelerating. Therefore, we have to have a balanced force diagram or no net force. If we were to consider breaking gravity into its components, again, you can tilt your paper till Fn is up and draw in your components of Fg. Here's my Fgy and Fgx. If you notice, my Fgx is 3 squares to the right. So my friction, which is parallel to the surface, will have to be 3 squares to the left. We would label that FFS for static friction. This is the only kind of new part, the idea of breaking gravity into components. The rest of the problem will still be the same method as we've used before. It asks, again, our original question is to find the value of Fn, find the value of FFS. It's given that the box of cake mix has a weight of 8.5 newtons. So that's our known value right there. This red vector, our force of gravity. It's asking for these two. If you're thinking about it, if we want to find Fn, we know Fn is equal to Fgy, and we know that our frictional force is equal to Fgx. So that's where our net force equation comes in. So for the vertical or perpendicular direction, again, I look at vertical as to when I put Fn facing the top of my page. The net force in that y direction is equal to Fn plus Fgy. The horizontal net force equation would be our kind of x direction or parallel direction is FFS plus FGX. Again, our main goal is finding these two values. We know the net force is 0 in both directions because the box is not accelerating. So that guides us to reason we need to find these two values. Horizontal and vertical components, again, are found with our trigonometry. So I redraw my angle or my triangle down here. There's one strange thing about this, is we don't necessarily have the angle given to us on a diagram like we normally do, but this angle is 20 degrees. There's a mathematical proof that would show a series of triangles that if this is 20 degrees, this is a 90-degree angle, therefore this would have to be 70 degrees. Additionally, if I were to draw another triangle like our component triangle we have, since this line is parallel to our ramp, this would have to be 90 degrees, this would have to be a complementary angle, so therefore this would have to be 20 degrees. So you can think through that logic each time if you want to find the angle, or as long as you draw the force of gravity components straight down and then either to the right or to the left, depending upon which way gravity is, you know that this angle will always match the angle of your ramp. So there's no need to show the proof for that, but you can just kind of keep that in your own memory. Okay, so FGY and FGX were our goals. I have an angle, I have a hypotenuse value, 8.5 newtons. So if I want to solve for FGX, FGX is the opposite side of my angle, so I will use sine. So sine of theta is equal to FGX over FG. Sine of 20 degrees is equal to FGX over our hypotenuse, which is 8.5 newtons. That gives us a value of FGX of 2.91 newtons. This is positive because it's to the right. We'll still use our positive and negative convention. However, you can have an argument about really this is at an angle. If you're looking at it, it's not necessarily one or the other. It's kind of down and to the right. But for our convention, we'll keep it as positive. So that's FGX. Now we want to find FGY. FGY is adjacent to our angle, so therefore we would use cosine. So cosine theta is equal to FGY over FG, our hypotenuse. So cosine of 20 degrees is equal to FGY over 8.5 newtons. You solve in your calculator and, oops, not the cosine. FGY is equal to 7.99 newtons. In our convention, though, FGY appears to be down. So when plugging back into your net force equation, you'll want to make sure that you have included that negative sign because FGY is down. All right, we did some work, we found our components, but we still haven't answered the question. FGX can be plugged in here, FGY can be plugged in here, and we can solve for our two variables. So the next question says solve for the normal force. I would remember my net force equation in the y direction is my normal force plus FGY. I'm not accelerating, so I have 0 newtons is equal to Fn plus, and then I have negative 7.99 newtons, which is what I just solved for. Add to the other side, and Fn is equal to 7.99 newtons. The next question says solve for the static frictional force. I have my net force equation in the x direction, FFS plus FGX. Again, I'm not accelerating. I'm looking for my static friction, and I know my component of gravity in the horizontal direction was 2.91 newtons. Subtract over, and your static frictional force is negative 2.91 newtons. So as you can see, from here on out, it was still the same solving problem method as we had used before, but instead of breaking Fn and FFS into components, we're only breaking gravity into its components. Why don't you flip to the back side, hit pause, and try to solve it on your own, and then check your work. Go ahead and hit pause. Okay, for this scenario, it's very similar to our first side. The 16 kilogram box is sliding down the ramp at a constant velocity. Constant velocity is still an acceleration of 0, so no net force, or our net force is 0. It says draw a force diagram and solve for the normal force and the force of friction. Hint, you need to find the force of gravity first for this one. It didn't give us a weight, it gave us a mass, so we will have to be solving for that. For drawing the force diagram, I first would look at the system, my box. I know that force of gravity is straight down. My normal force is perpendicular to the surface. And my frictional force is parallel to the surface and opposite the direction of motion. So it's moving this way, so therefore my friction has to be this way. I tend to draw it on the diagram to help me see the relative sizes. So if I redraw this, I should be able to recreate those angles pretty well. Again, this is that tricky part where instead of tilting or breaking my Fn into components and my FFK, that's just too many unknowns for us right now, I need to change my frame of reference till Fn is up, draw my components of gravity, and realize Fg, the full resultant, will always be the hypotenuse. So this is the 90-degree angle right here. Sometimes people try to draw this as a 90-degree angle, but remember the resultant has to be the biggest one. This is FGY, FGX. So the first step here, if you're just kind of thinking about what you need to do, would probably be to solve for the force of gravity. I could write my net force equations to kind of guide my thinking. My net force in the y direction is equal to Fn plus Fgy from these two. I know that those two have to be equal. The net force is 0, and they're the only two vertical forces. I have a net force in the x direction, which is equal to Ffk plus Fgx. And now this is reminding me that I need to solve for my components of gravity to find these two. I know these are 0. I have to find these before I can calculate those. So, looking at our triangle again, we know this is 40 degrees. I tend to redraw that triangle just to help myself visualize it. And we go through it and we say, oh, our hypotenuse, it's not 16 kilograms. It is actually, that's the mass, so we need to find Fg. And how do we find Fg? That's the one we have an equation for. 9.8 newtons per kilogram times mass. So 9.8 newtons per kilogram times 16 kilograms. And our force of gravity is 156.8 newtons. Now I can use that as my hypotenuse. So to solve for the components of gravity. With my triangle, I see that my opposite side of the angle, or of 40 degrees, is FGX. So the sine of theta is equal to FGX over FG. Sine of 40 degrees is equal to FGX over our FG value, which we calculated as 156.8 newtons. So our FGX, if you solve in your calculator, is equal to 100.79 newtons. The other component, FGY, is adjacent to the angle, so cosine of theta is equal to FGY over FG. Cosine of 40 degrees is equal to FGY over, again, our weight of 156.8 newtons. So FGY is equal to 120.12 newtons. If I'm looking at this on my diagram, I have to realize that FGY is down, so therefore that would be a negative value. I'm still not done, as you'll see that I have FGY and FGX, but it asks me for Fn and FFK. So within the net force diagram, the net force equations, the net force in the y direction is equal to Fn plus Fgy. I know this value is 0 newtons. And Fgy was negative 120.12. Add over to the other side, our normal force is equal to 120.12 newtons. Additionally, to find my frictional force, net force in the x direction was FFK plus FGX. Again, 0 newtons due to no acceleration is equal to FFK plus 100.79 newtons. Subtract to the other side, our frictional force is equal to negative 100.79 newtons. So these two are our answers for the problem. Below, there's just a quick question to kind of remind you. So when objects are placed on an incline, is the force of gravity always equal to the normal force exerted by the surface? And the answer would be no. You only see a portion of gravity being equal to the normal force. Obviously, there are situations where I could have more than one force in this vertical direction where it could cause it to be the same, but generally that is an assumption that they are not the same, or I guess you can't make the assumption that they're the same without knowing more information. All right, enjoy practicing those other problems. As always, try to ask for help if you are still very stuck. Goodbye.